All right, hello everyone. So let's go through this particular question for Hardy-Weinberg. In a certain population of people, 36% of the population is born with sickle cell. So it's a disease that's homozygous recessive. So these individuals that have the disease are homozygous recessive. What percentage of the population would be found in the heterozygote form, giving them a selective advantage in areas of malaria? That's secondary information. Assume the population is in Hardy-Weinberg equilibrium. Again, pause the video here, try to figure it out, and I will go through the question in a short bit. So I'll see you back here potentially in a couple of minutes. All right, hello, welcome back. I hope you paused the video and actually try to solve the question itself and figure out what the answer is. And, well, we're just going to go through it now and see if you got the correct answer or not. Okay. So again, this is a very interesting question because you're going kind of backwards in a way. You know that the population is already in Hardy-Weinberg equilibrium, so you're just trying to solve something else based on your knowledge using the equations that you know before, given some kind of a variable that's available. So in our case, we're trying to find the number of heterozygotes in the population. So we're looking for the genotype frequencies. So first of all, we know that in our case, let's just use big A, little a again, just to keep things going a little bit straightforward. Again, you can use whatever letters you want in our situation. I just decided to choose big A, little a. So in my case, the little a I made to be the genotype frequency of individuals with sickle cell disease. So we know that little a is equal to Q squared, which is in our case equal to 36%, which is 0.36. So we want to turn it into a decimal, which is just divided by 100. That's, I think, pretty straightforward. So we know that Q squared is 0.36 because that's the frequency of individuals with sickle cell disease, which is homozygous recessive, and we're looking for the heterozygotes. So we know Q squared is 0.36. We can easily find Q by square rooting 0.36, which will give us 0.6. So our Q value is 0.6. Now looking for the number of heterozygotes here, which is found via the equation 2pq, remember 2pq is finding the frequency of the number of heterozygotes in the population, we can use 2pq. We know what the Q value is, so we can find the P value because, again, our population we know is in Hardy-Weinberg equilibrium, so we can use those equations. So remember that P plus Q equals 1. So that means that P equals 1 minus Q. Think about that for a second. Hopefully it makes sense. And so we know that P equals 0.4. Q is 0.6, so P obviously is going to be 0.4 if they're going to add up to 1. That should make a lot of sense to you, I hope, at this point. So just, again, these are things that should just build up in your brain over time, and you should get to kind of recognize some of these patterns and trends across these Hardy-Weinberg questions. So we know our P value, which is going to be 0.4. We know our Q value, which is going to be 0.6. Remember that our A is going to be 0.4. Our little a is therefore going to be have a frequency of 0.6. So our allele frequencies are big A 0.4, little a 0.6. These are going to correlate with P. This is going to correlate with Q. And so we know our P and Q values. We now can find the number of heterozygotes, or the frequency of heterozygotes. So 2pq is going to be used to look for our heterozygote frequency. We know P is 0.4, we know Q is 0.6. Heterozygotes big A, little a, that's equal to 2pq, which is therefore just going to be 2 times 0.4 times 0.6, which is 0.48. And of course, we're looking for what percentage according to the question. So we have a decimal, you just multiply it by 100. And so the percentage of heterozygotes, aka heterozygous individuals within this population, that ultimately will have a selective advantage in areas with malaria, will be 48%. And again, this is a working backward type of problem where you know that it's in Hardy-Weinberg equilibrium, and they're giving you some kind of a variable, some kind of parameter that you can use to help figure out other things like other allele frequencies and other genotypes. So I hope that makes sense, and I hope that this series of videos have been helpful to you. Please go to office hours and go ask your professor, your learning assistants, your student tutors, and they can help you as well in getting a better hang of this fairly tricky but perhaps not so difficult concept of Hardy-Weinberg equilibrium. So best of luck studying, and I'll see you all in the next video. Thanks.